Sir, should I share the entire screen, right?
Yeah. Window.
You can share, sir. Huh?
Window na share.
What was this?
No, I opened the PPT and
Then go for.
Please click present now, sir.
yeah, present now I clicked, and then there are three options: your entire screen, window, and tab.
You select Windows, sir.
Window, okay. Then
Click on that PPT.
no, it's not coming. That's what I'm seeing. I'm not getting that.
Sir, you just close and open that same PPT, sir.
Okay. I might have opened it beginning, right? Yeah, 2 minutes.
Yeah.
Yeah, it's come. So might be I have opened this before we start this session.
Yeah.
That's the reason I think.
You click present now.
Yeah, 1 second.
A window.
Yeah. A window, and then I can
Click on that PPT, sir.
yeah, it's coming.
And then share.
Yeah. Can you see the PPT?
Yes, sir. We can.
Yes, sir.
It's in PPT mode, right?
Yes, sir.
Yeah.
Full.
Okay, sir. Sorry for the initial glitch.
No, sir.
So once again, I thank the organizers for this opportunity. Today I'll be talking on the numerical solutions of PDE, and in particular, I will be focusing on finite difference methods. So this is a more general title. So when you talk about the numerical solution of PDE, there are several methods available to solve PDE. Out of this finite difference method is one of the pioneering method to find the approximate solutions of a partial differential equation. So I will be sticking on to only the finite difference method, though there are plenty of other methods available, and latest developed methods are also available. So this is our campus. It's not a Photoshop. It's a real photograph of our university front view. And this is the content. So today, the topic of the FTP is recent trends in fluid mechanics. So generally, when you try to analyze the problems in fluid mechanics, there are two ways. One is you have to perform experimental, or we call it as experimental visualization. The another one is theoretical calculations. So when we do theoretical calculations for problems or for situations in fluid mechanics, we'll end up with mathematical equations which represents the physics behind the actual process that we have undertaken. So as a mathematician, our role is to solve the resulting mathematical equations which will give the solution for the actual physical problem. In this lecture, I will be focusing more on mathematical aspects of solving a physical problem arising in fluid mechanics. So because of that, so these are the basic contents. So this is the plan of my talk. First, I would introduce the basic concepts of differential equation, why we need to solve a differential equation, all those things. And then I introduce the finite difference method. Then I will take one research problem where I applied the finite difference method to solve the fluid flow and heat transfer characteristics using finite difference method. So let us start with a positive note. Generally, what happened, being working in an engineering college, the engineering students always don't like much mathematics. So this always tell that the essence of mathematics is not to make simple things complicated, but it is the other way. So I try to reduce the complicated things into a simpler one. So as I said, whenever we encounter the methods of predictions, and there are basically two types. One is you have to go for an experimental investigation or you have to go for a theoretical calculation. That's where the numerical simulation comes into the picture. So just briefly see what these two techniques or these two ways of analyzing a particular problem. So when we talk about the experimental investigation, there's no doubt that the experimental investigation gives the most reliable information, provided everything goes well, that instrument is working fine and we take the calculations. So the input in general, it's free from all kind of errors. But sometimes when we thought of, there are some situations where the full scale experiments are highly expensive or sometimes even impossible, which means when you want to design experiment which is involving a large scale, okay, so people see there, we are not sure that the experiment will be success or not. So the alternative is to perform a small scale model. We call it as a prototype model, and of course this prototype model will not have all the features of the full scale experiment, but it will be a miniature size of the actual one, and that will be tested in the laboratory experiments, which we call it as a wind tunnel experiment. And once we get the satisfying results, then that we generalize to the actual one. So these are the difficulties associated with the experimental investigation. On contrast to this, when you look at the theoretical calculation, so in theoretical calculation, we don't work on the actual problem, but we work on a mathematical equation which comes out of the mathematical modeling. So generally, mathematical modeling, the layman definition is a simple transformation of physical laws into the language of mathematics, and the end product will be a set of mathematical equation, which can be a simple algebraic equation or a transcendental equation or a system of a linear or nonlinear equation or a ODE or PDE or any kind of mathematical equation. And as a mathematician, our task is to solve the resulting mathematical equation. And many times when we do the mathematical model, the mathematical model mainly consists of a differential equation or a set of differential equation. For example, in the case of fluid mechanics and heat transfer, we have three basic conservation laws of a law of conservation of mass, conservation of momentum, and conservation of energy. So here we get a system of equations, partial differential equation, and that has to be solved to get the fluid flow and the heat transfer process for a particular situation. And when we do a mathematical modeling and the end equations, the mathematical equation what we get are highly complex in nature. So the traditional mathematical techniques cannot be applied to solve such kind of differential equations. So the alternative is to go for the numerical solutions, and that's where the the essence of this lecture lies. This is just a brief overview of the two kind of techniques that is available to analyze a given problem and a given situation. So when we talk about the mathematical modeling, the first question comes into our mind is why we need to do model, or what is the purpose of model. So basically the model is to gain the understanding of a particular phenomena when there are no other alternate ways to study that particular phenomena. See, generally, even if we want to go for an experimental analysis for a particular situation, you just think of two situations where the first situation you are directly going for the experimental analysis for the given situation, and the second situation is for the same analysis you performed already a mathematical modeling, and through modeling you have some information about that particular system, and then with that system you are going to design, or you are going to do some experimental analysis. So definitely the second situation would be much comfortable for a design engineer, for experimentalist in general, because he has some knowledge of that particular experimental system where he is going to perform. Okay, and as I said, the second important purpose of a mathematical model is to predict what's going to happen to a system, or you generate numerical simulations for a particular physical problem. So with these two major motivation or major aims of mathematical modeling, and that is where, see, because when we, as a mathematician, when we do mathematical modeling and if we provide solution for a particular situation, it would be more helpful. It's something like something is better than nothing. That means you are going to perform an experiment without having any information, but you are going to perform an experiment with some information in your hand about the system what you are going to investigate. So this is the main purpose. So generally, as I said, a mathematical model is a representation in terms of mathematics of certain aspects of a non-mathematical system. Very nice definition. See, when we try to do a mathematical modeling of any physical system, that system is basically governed by some physical laws. It's not governed by any mathematical equation that you are converting into the language of mathematics, and that the end product will be a mathematical equation. So generally, we can transform the laws associated with the branches of physics, chemistry, biology, engineering, etc. and in terms of mathematical expression. So if you look at the modeling, we have always two disciplines involved. The first discipline is mathematics, that is always fixed, because that is, so here mathematics we use as a tool to solve the problem arising in mathematical modeling. The second group is a discipline. So I can, as a mathematician, I can associate with a physics department or a chemistry department, a biology or any engineering department, or any medical, even a medical also. Now we have artificial, limb, artificial synovial joints we are preparing through mathematical model and 3D modeling. So the mathematician can be associated with any other discipline, and when I associated with a physics department, we can call it as a mathematical modeling in physics, and similarly chemistry, modeling in chemistry, like that. So this is a brief idea of mathematical modeling, and these are the steps when we try to involve when we try to solve a problem using mathematical modeling. So this is the general steps involved. You identify the physical problem, and in that physical problem, you have to identify what are the important variables. For example, in flow problems, we need to determine what is the velocity in different directions and what is the pressure. And if I take into account of the temperature variation, I need to identify the variable which relates the temperature. And you apply the relevant physical laws for that particular physical situation to reduce the physical problem into a mathematical problem. And then you see the complexity of the problem. If the mathematical equation can be solved in its original form, well and good. Otherwise, you make some reasonable assumption and approximation to reduce to a situation where the problem can be able to solve. So we assume that the mathematical problem or mathematical modeling reduces to a differential equation. So once we have a differential equation, we need to look at the behavior of the differential equation, and based on that behavior of the differential equation, we choose a solution technique. And any differential equation cannot be solved without having initial or boundary conditions. So we have to choose an appropriate conditions, supplementary condition, which is the main crux of any problem, and then we find the solution. So this is the, what do you call that, the flow chart involved in mathematical modeling. Okay, so we'll go with the very basic definition of what is differential equation. So differential equation is basically an equation involving some unknown function and its derivatives. So based on the nature of the unknown function, we call the differential equation is ordinary differential equation or partial differential equation. Suppose the function depends on only one independent variable, we call it as an ordinary differential equation. If the function depends on more than one independent variable, we call the differential equation as partial differential equation. As I said, see, I assume that in mathematical, see, in general, when we do mathematical modeling, the end product need not be a differential equation. It can be any mathematical equation. So I here restrict, or I assume that when I do mathematical modeling, or in particular in my area of research, I'll end up only a partial differential equation or an ordinary differential equation for a simplified situations. So, as I said, before we choose the solution technique, we must know the behavior of the mathematical equation. So, in particular here, the partial differential equation. So, when we have a partial differential equation, the partial differential equation broadly behaved in three different ways: elliptic, parabolic, and hyperbolic nature. So, in this particular differential equation, I assume that the coefficients A, B, C, D, E, F, and of course G, they are all constants. They can also be a functions of the independent variable. That's a different case. We just, for this classification, we assume that those coefficients are just of constants. There are two other cases. They can be a function of the independent variables, and they can also be a function of the dependent variable and or their derivatives. So in that case, we call the differential equation as a non-linear differential equation. Okay. So now, if we assume the coefficients are constants, then the differential equation can be called as elliptic if this quantity called b squared minus 4ac is less than 0. If it is equal to 0, it's a parabolic, and if it is greater than 0, we call it as hyperbolic. See, what does it mean? Elliptic means we generally say that the differential equation is independent of time. It's a kind of stationary problem. Okay, and parabolic and hyperbolic. Okay, in particular, parabolic, it's time dependent, or there will be a time-like variable, which means you need to march the solution in that particular direction. It can be either time or time-like variable. Okay, and hyperbolic, see, parabolic and hyperbolic, there will be time will be involved. Okay, and in hyperbolic, generally the kind of problems which involves wave phenomena or wave kind of phenomena will be classified into, or can be put into, hyperbolic type of partial differential equation. So I said these coefficients can also be a functions of the independent variable. So now, if the coefficients are only constants, then the PDE can behave like either elliptic or parabolic or hyperbolic. That means in a given domain, it can be only elliptic, or it can be only parabolic, or it can be only hyperbolic. But if the coefficients are functions of the independent variable, then I can find the two or all the three behavior of the PDE for the given domain, which means at some regions of the domain, the PDE may behave like elliptic, and some other region it may behave like parabolic, and some other region it may behave like hyperbolic. This is possible only when the coefficients are functions of the independent variables x and y here. Okay, so this classification is important again. Why? Because this classification of the given PDE helps us for the choice of the numerical method that we adopt to solve the given PDE. So that's why it's always better to have identify the nature of PDE. And further, we classify the PDE into the further types: homogeneous and non-homogeneous. So in homogeneous, the PDE, we say that in a simple way, if G equal to 0, we say that the PDE is homogeneous. If G is not equal to 0, it is non-homogeneous. What does it mean? So when, see, G can be, again, G is a constant, let us say. In a differential equation, if all the terms, contains either the dependent variable or any of its derivatives, then such a differential equation is called as a homogeneous. If I can identify a term which is free from the dependent variable and or its derivatives, then the differential equation has to be called as a non-homogeneous partial differential equation. Okay, and then again linear and non-linear PDEs. So the linear PDE means here the partial differential equation. Thank you. Sorry. So linear, non-linear partial differential equation. So linear partial differential equation means generally the dependent variable, the power of the dependent variable should be same throughout the differential equation, and the differential equation should not have the products of the dependent variable and or its derivatives. So if any one of the condition is violated, then the differential equation has to be called as non-linear differential equation. And as I stated earlier, a differential equation cannot be solved without any some supplementary conditions. So based on the way we supply the supplementary conditions, the differential equation along with the conditions will be called as a boundary value problems or initial value problem. Sometimes we'll have initial and boundary value problem. So generally we say if the boundary conditions are specified at one particular point, then the problem will be called as an initial value problem. And if the conditions are specified at more than one point, then the differential equation along with the problem will be called as boundary value problems. Generally, when we end up with a mathematical equation, we must ensure that the problem is well posed. So what do you mean by well posed? In 1902, Hadamard, a mathematician, defined what do you mean by a well posed problem. The problem is well posed if these following conditions are, three conditions are satisfied. First and foremost, the solution of the problem must exist. And it's not the solution just exists, the solution must be unique, which means I cannot have more than one solution for that particular problem. And the solution should also continuously depends on the supplementary data, that is the initial or boundary conditions. So if these three conditions are satisfied for a mathematical problem, then we say that the problem is well posed, otherwise it should be called as ill posed. And many a times the ill posed problem can be converted into a well posed problem by making this remedy. Problem needs to be reformulated for considering the numerical treatment, and sometimes we need to add additional constraints. For example, we need to smooth the solution of the given problem, or we may need to regularize the input data, or we have to pre-process the solutions. So these are some of the remedies. As I said, when I want to solve a partial differential equation, we need to have a supplementary conditions. So, as I said, there are two ways to solve the problem. One is a boundary value problem, another is initial value problem. In boundary value problem, the conditions are specified at more than one point, and the way we specify the conditions, there are two ways. One is you have to specify the unknown along all the boundaries. For example, in the rectangular box, left and right wall and top and bottom walls, I just specify the unknown values. Okay, that is called as Dirichlet boundary conditions. There are situations where you need to specify the normal derivative of the dependent variable along the boundaries. For example, in the case of fluid dynamics, because we are talking about the FTBs on fluid dynamics, so there is a concept called no slip and no through flow condition. So when you talk about no slip, you get Dirichlet boundary condition. When we talk about the no through flow condition, which means that means when I talk about the velocity in terms of stream function, then you get von Neumann boundary conditions. So this is the rough structure of the boundary value problem. So you have a boundary, an arbitrary shaped boundary, where the solution along the boundaries are known. And using those values, you are supposed to find the solution inside the boundary. This is the way the boundary value problem works. An initial value problem, as I said, the conditions are specified at only one point. So here, again, you can specify the initial condition with the help of the unknown, or sometimes we need to specify the first order time derivative of the dependent variable. And this is called as a one Newman. So this kind of condition where the derivative of the dependent variable with respect to time, if you are specifying, so that kind of situation happens in wave phenomena, okay, or we can say in mathematical way, hyperbolic partial differential equation, you need to have such kind of conditions. So this is how it looks like. So along the initial value and along the boundaries, you have the solution from boundary condition, and we need to march. For example, in time dependent variable, I know what is the solution of the differential equation at time t equal to 0, which is called as initial time. And along the boundaries, we get the solution from the boundary condition, and we need to march the solution with respect to time. For time t greater than 0, what is the solution? So that is how the structure of initial value problem works. So at time t equal to 0, I know my solution, and using that, I must find the solution of the differential equation for all time t greater than 0. So when we talk about the condition, boundary condition, apart from the von Neumann and Dirichlet condition, we have another boundary condition known as Cauchy's boundary condition. This is just a combination of both the boundary condition, that is von Neumann as well as Dirichlet condition. And generally, when we are solving a partial differential equation, we must know that suppose if you are solving an nth order differential equation that will have n arbitrary constant, so we must have n supplementary conditions to solve an nth order differential equation. And when we come to the numerical solution of PDE, see, generally we classify the solution into two types. One is analytical technique, another is numerical technique. So there's no doubt that analytical technique or analytical solutions, which we also called as an exact solution, is the most powerful solution because that is available in the solution domain continuously. But whereas a numerical solution, which is an approximate solution only, it is not a continuous solution, it's a discrete solution. That means in your solution domain, particularly with the finite difference method, you are finding the solution only at the selected number of grids or grid points. That's why it's called as an approximate or numerical solution. But unfortunately, all the partial differential equation cannot be solved to get the exact solution. And when we go for an approximate solution, we cannot find an approximate solution by just using only pencil and paper or an electronic calculator. See, when sometimes we may need to solve a very large system of equation, let us say 101 by 101 or 201 by 200 system, depending upon the complexity of the problem that we have undertaken. So such kind of high speed, such kind of the inversion of a large number of system of equation is highly impossible to do the hand calculations. So in such situations, we may need to go for the high speed computers or at least a good computers to get the solutions of such kind of problems. So this is a very important, concept where we have to go for, whether we have to go for a numerical technique or we can restrict ourselves only to an exact solution. See, when we do mathematical modeling, we'll end up with a complicated mathematical equations, which cannot be solved. So if we want to solve, or if you want to find an exact solution for the that kind of equation, we may need to use some approximation so that the complex mathematical equation reduced to a form which can be solvable using any of the traditional techniques, so that I'm getting the closed form solution or exact solution. The other situation is I'll keep the original differential equation which I'm getting out of mathematical modeling as it is, but I will find out the approximate solutions. So with this, we have two situations. Whether I want to go for the exact solutions of an approximate equation, or I'm going for an approximate solution of the exact equation, the original equations. So in our this today's lecture, we are following the second one, later part, where we are finding the approximate solution of exact differential equation. Okay. So what is the use of numerical methods is, though analytical solution is the most preferable, it is not possible to get the analytical solution for all problem arising out of the mathematical modeling. And so we have to go for the numerical solution. Another situation where you have the data of the dependent independent variable in the form of a table or a tabular form. In such case, if you want to find the derivative, or you want to find the integration of the relationship between the dependent and independent variable, which cannot be performed with the traditional method, so you have to go for numerical differentiation and numerical integration. And this is the purpose of why we have to go for numerical methods. So there are many methods: finite difference, finite element, control volume, and now we have meshless, and we have lattice Boltzmann. And recently, people are using combining, means they pick the advantage of one method and advantage of another method, and they combine, and they replace the disadvantage of one method with the advantage of another method, which we call it as a hybrid method. So among all the available technique, the father of the numerical technique is a finite difference technique. It is one of the oldest method adopted to solve the differential equation. And whatever may be the method, even the recent method, the method has to be tested for its consistency and stability. And that's a very important, because a scheme which is not stable and which is not consistent may not produce a realistic solution. We may get a solution but that may not be the solution for the problem that we have undertaken. So we must be very cautious while choosing the method. So if you look at the finite difference method, the basic idea of finite difference method lies on the very basic definition of the derivative. So if you look at the derivative, du by dx, or u dash of x, so left hand side we have a derivative. This is I'm talking about with respect to the basic definition of the derivative. And if you look at the right hand side doesn't have the derivative, but we have the function value at two different or neighboring points, the difference between the function value at two neighboring points. And this is true only when the delta x, the difference, is very small. So the basic definition says that the derivative can be expressed as the difference between the function value at two neighboring points, provided the two neighboring points are very close to each other. So using this basic analogy, the finite difference method has been developed. So there are 4 steps involved totally. The first one is we have to discretize the computational domain that we are dealing with, and the partial derivatives appearing in the differential equation has to be replaced with the appropriate equivalent finite difference approximation. And once it is done, then we have to do the rearrangement. And means we have to order the finite difference equation so that you bring into a particular structure, and then that gives rise to a system of algebraic equation that has to be inverted. So in any case, the partial differential equation or ordinary differential equation, when you are trying to solve a finite difference method, you are just converting into a system of algebraic equation and then you are solving it. So this is let us say this is my physical domain which I want to, where your differential equation is defined in this domain, and I want to solve it by finite difference method. So what we do is we just draw lines parallel to the coordinate axis, namely here x and y, and the intersection point uh, between these two lines are called as the grid points or mesh point, and we are finding the solution of the given differential equation only at these points. So here the distance between two grid points are called as the grid space or mesh space. Generally, the grid spacing need not be same, but it can also be same. So I just take a particular grid, general grid. Say, for example, here I comma j is the general grid structure, where I is the index we use along the x-axis, and y is the along the y-axis we use the index j. In the positive x direction, I will be increasing, and negative x direction, I will be in the decrement. Similarly, in the upward and downward, the j will be increasing and decreasing respectively. As you can see that you have delta x and delta y. Delta x is called the mesh spacing in x direction, and delta y is the mesh spacing in y direction. So in general, these two spacing need not be equal, but it can equal because that depends on the situation that we undertake. Okay, and so here main thing is when you suppose you have u of x comma y, u is a function of x and y, then the x and y will be replaced by the indices I and j. So I space stands for the x value and j stands for the y value. And here we want to, I'll be showing how to derive the finite difference approximation. There are many ways to derive the finite difference approximation. One of the popular way to derive the finite difference approximation is to use the Taylor series expansion. So here, if uij is the x component of velocity at the points I comma j, and ui plus 1 is the point at the I plus 1 comma j. I plus 1 means u of x plus delta x comma y. Uij means u of x comma y. Okay, it's like that. So when you expand the Taylor series expansion, we get this. That is the equation, first equation. And similarly, when I go for the Taylor's expansion of ui minus 1j, this is what I get. Okay. Now, the above expansions are mathematically an exact expression for ui plus 1 and ui minus 1, provided these two conditions are satisfied. The first thing is the number of terms are infinite and it's a convergent series. The Taylor series must be a convergent series. The second and most important thing is my delta x must be as small as possible. So here, because I'm considering delta x is very small, your delta x squared will be further small. So I'm just neglecting delta x squared and higher order terms. So which results a finite difference approximation, we call it as first order forward difference approximation. Similarly, this Taylor series approximation, if I neglect delta x squared and higher order term, I get a backward difference. Similarly, if you subtract, I'll get central difference. So for a first order derivative, I have three different finite difference approximation: forward, backward, and central. So these difference approximations are used depending upon the situation and requirements of the partial differential equation. And similarly, we have a finite difference approximation for a second order derivative, which is called a second order central difference. So among the three difference approximation for the first order finite difference approximation, forward and backward is a first order accurate, whereas the central difference is a second order accurate. That means the error produced in the central difference is minimum compared to the error produced in the forward and backward. So whatever the derivative that you derive, there is a finite difference approximation of the partial derivative with respect to x. So if you look at there, the index I will be changing, and with respect to y, the index j will be changing. So which means, see, in the partial derivative with respect to x is the variable, and partial derivative with respect to y is the variable. So accordingly, your I and j keep changing. And this is the final difference approximation for higher order derivative, because sometimes some modeling we may also encounter a partial differential equation which is of higher order, which has higher order derivative. And this is the final difference approximation for mixed order derivative. And when you look at the final difference technique, it broadly classified into two different ways. One is an implicit final difference technique, another one is explicit final difference technique. I will be explaining both the technique with the help of one-dimensional heat conduction equation, that is del U by del T equal to alpha into del squared U by del X squared. So alpha is called as thermal conductivity of a solid rod. So you can imagine that we have a rod where the heat is traveling along the x direction, and it is depending upon time. And if you look at the equation, you have first order derivative with respect to time and second order derivative with respect to space, and therefore we must have three conditions. So one with respect to time, and there are two conditions are required with respect to space. So because it's a time dependent problem, we need to specify what is the initial temperature of, here U is the temperature. What is the initial temperature of the rod? So here if you see U of x comma 0 equal to f of x, which means at time t equal to 0, what is the temperature of the rod at different locations of x? That is given by the first condition. And the second condition and third condition, if you see together, they are nothing but the temperature of the rod at the initial and end locations of the rod. So that is true for all time. For all the time, we are maintaining the same temperature of the rod at the end locations. So this is how the boundary conditions for this particular problem, and this can be generalized to any partial differential equation. So if you look at the grids structure, this is how, see, actually it is not, it looks like a two-dimensional, but it is not, because the y-axis is a time axis, which is an imaginary axis. So you can imagine you have a rod, okay, so where you have to find the temperature of the rod at different locations for different time levels. So what we do is we fix a time, let us say t equal to t naught. At t naught, I know what is the temperature of the rod from the initial condition. Then I go for the next time level, t1. At time t equal to t1, I will calculate the temperature of the rod at all locations of the rod. Then I'll go for time t equal to t2. So that way, if you look at, t is not the actual dimension, it's an imaginary dimension. That means we need to perform we need to get the temperature of the rod at different locations for different time level until we reach a state where the temperature of the rod does not vary with respect to time. So that's why. An explicit method, this is a partial differential equation where u of x comma t is given by uin. So x is corresponding to I and the superscript n corresponding to time. So we apply forward difference for the time derivative. See, gain. I said there are three final difference approximation: forward, backward, and central. So I cannot apply forward difference, I'm sorry, backward or central difference here, because that will lead to an unknown time level where you will not get the conditions. So normally the time derivative will be replaced by forward difference, and here the second order spatial derivative will be replaced by the second order central difference. So this is what we got, and when a simple rearrangement gives you a final difference equation like this, and then if you further rearrange, because you have ui and you have ui, so we rearrange the final difference equation like this. You have I minus 1, I plus 1. If I have j, then I minus 1, I plus 1, j minus 1, j plus 1. So this is how the arrangement should be. So here I introduced a parameter called Sx, which is called as the mesh ratio parameter, okay, which is alpha delta t by delta x squared. Now this particular scheme is called as explicit method, and this is called as FTCS scheme, that is forward time centered space. So let us see here why this explicit mean. We are getting the unknowns from the values of the known. So such kind of, that means I'll get a solution at a grid point, then I'll use it to find the solution at the next grid point, then I'll use the solution of the previous grid points to find the solution of the next grid point. So as a picturization I just given here. So think that this is a rod, okay, and this is the dots or the solution coming out of the initial condition, and this is the vertical dots or the solution coming out of the boundary conditions. So what we do is, you can just see, I'm just getting the solution one after another. This is what happens in a explicit solution. See here. So that means when I complete this level, okay, when I complete this level, I complete one time level, and then I'll go for the next time level. Okay, and once I complete the next time level, I'll compare that current level with the previous time level, and if the difference is less than the pre-specified tolerance value, I'll stop my calculation and I claim that I have reached the steady state. If not, I go for the next time level and do the same technique. So every time level I complete the calculation, it's my duty to check for whether I have reached the steady state or not by comparing the present level solution with the previous time level solutions. So this is a calculation procedure in the system. So this part, let me skip. So this is important because I mainly focus on the kind of type of finite difference approximation that we use. And as I said, any finite difference approximation should be checked for the stability. There's a von Neumann stability analysis. This says that this scheme is stable only when this condition is satisfied. That is, the mesh ratio parameter should be less than or equal to 0.5. If we violate this condition, then the scheme may produce a spurious solution which may not be realistic. I'm just giving an example of unstable calculation. See here at the nth time level, the temperature is 100 degree, 0 degree, 100 degree, and I want to find the solution at the next time level, that is n plus 1. And purposefully, I'm just violating the stability condition, and we'll see what happens. So I'm just choosing Sx equal to 1. Okay, I'm just choosing Sx equal to 1. As the law, it should be less than or equal to 0.5. When I choose Sx equal to 1, I'm getting the temperature at this particular case is 200 degree, which is not realistically correct, which is realistically not correct. Which means when I have a boundary temperature, the interior temperature must be less than the boundary temperature, unless otherwise I have some heat generating substance inside the rod. And I don't have anything because this is the one-dimensional heat conduction equation I use, and which doesn't have any other extra term. So this spurious solution, I got it just because I did not meet the stability restriction or condition posed by this. So this is a severe restriction on explicit method. And when you look at the implicit method, that the only difference is I'm discretizing at n plus 1th time level. And when we follow the same thing, forward time centered space, I get a finite difference equation like this. Okay. So here, if you see the left hand side, we have more than one unknowns. Right hand side, we have only one unknown and one known. So because of this, you cannot get the solution by point, but here you have to solve a system of equations. So generally, an implicit method solving a problem, you need to solve a system of equation that comes out of every time level. I just explained here. So these are the boundary and initial condition. And you can just see that along the rod, I have the circles are blinking, which means those circles represents each circle will give us, that means at each grid point, it's a grid point. At each grid point, I'll get one finite difference equation. So here you'll get 5 by 5 finite difference equation, which has to be inverted simultaneously. So when I'm trying to solve an implicit equation, I need to solve a system of equations arising. Okay, so that's the main difference here. So generally, when we use the finite difference implicit method, we get a banded matrices. Sometimes we get a tridiagonal matrix. Sometimes we get a pentadiagonal matrix. So when we get a tridiagonal matrix, we have some well-known algorithm known as a Thomas algorithm, which easily inverts the Thomas tridiagonal matrix, because the advantage of the tridiagonal matrix, the Thomas algorithm is, see, in the matrix, there are only 3 diagonals. There is main diagonal, subdiagonal, and super diagonal, are filled with non-zero elements. All the remaining places are filled with zeros. So what happened? This particular algorithm doesn't take into account of the remaining portion. It takes account of only the elements which are located in the main and super and subdiagonals. So because of that, the computer time evaluation is much less compared to the other algorithms. That way, this Thomas algorithm is much familiar and well known. And if you look at the von Neumann stability analysis, we say that the scheme is unconditionally stable. There is no stability condition, unlike your explicit scheme where you have Sx must be less than or equal to half. Okay. And among the implicit method, one of the popular method is the Crank-Nicholson method. The advantage is it has higher order accuracy than the normal implicit method. So what we are doing is we are discretizing the partial differential equation at the midpoint of the time level. We have explicit method, we discretize at the nth time level. Implicit method, we discretize at n plus 1th time level. Here, we discretize the differential equation at the n plus half time level. And when we do that, left-hand side, we apply the central difference scheme. It's a central difference scheme. And right-hand side, it's a central difference scheme at average of nth and n plus 1th time level. Okay. So this derivative can be written as average of this derivative at nth time level and n plus 1th time level. And that's how you get this. And when you rearrange it, you get again tridiagonal structure. And the main advantage is the error, truncation error is delta t squared and delta x squared. That means second order in space as well as time. But whereas a normal implicit method, it is first order in time, second order in space. And this is a very popular method. So the implicit and the explicit has both advantages and disadvantages. That mainly depends on the severity of the time levels. And suppose if you consider a two-dimensional equation, see, when you go for an explicit scheme, definitely it poses a severe restriction, particularly for a multi-dimensional problem. And if you go for a Crank-Nicholson method, it produces a pentadiagonal matrix rather than a tridiagonal matrix. So the alternative is to go for time-splitting algorithms. And one of the most popular algorithm is the ADA method, that is alternating direction implicit method. So according to this, the method will be implicit in one direction, and in the first half time. That means the actual time step, that is n to n plus 1, is divided into 2 half time steps, n to n plus 1, I'm sorry, n to n plus half, and then n plus half to n plus 1. That means instead of traveling from n to n plus 1, we first travel n to n plus half, then from n plus half to n plus 1 we travel. So each half time step, the method will be implicit in only one direction. And because of that, we ended up with a tridiagonal matrix, which can be efficiently solved by Thomas algorithm. And this method was developed by Peachman and Rashford. This is how the ADA method works. So here you see that I'm considering x direction to be implicit. So I'm discretizing at the advanced time level n plus half. And here star denotes the derivative at n plus half time step. So when you rearrange it, this is what the final difference equation we get, and this is the tridiagonal matrix. So this tridiagonal matrix can be efficiently solved by Thomas algorithm. So if you look at this, there's a sweep in this direction. There is two sweeps will be there. One sweep will be along x direction, another sweep will be y direction. That happens in each half time levels. And second half times level, I will be making the y direction to be implicit, and when you discretize, you get a final difference equation like this, which can be solved again by Thomas algorithm, and this time the sweep will be in other direction. And the formal truncation error of this method is first order in time, second order in space. Again, this the scheme is unconditionally stable, and this method is the most powerful method to solve the multi-dimensional problems. So this is the actual grid. So this will be implicit in x direction. So there will be sweep in the x direction, and the sweep will be in other direction. And let me skip this because see, generally what is this particular part is see, sometimes what happen if we cannot adopt to any of these standard techniques. Sometimes we need to solve the final difference equation by using iterative solution technique. Hello? Sir, another 2 minutes, sir.
You can continue, sir. Another 2 minutes, no problem.
So these are the different iterative methods: Jacobi, Gauss-Seidel, and successive over-relaxation. Okay. So generally the Jacobi iteration, it's just a plain iteration which will not use the updated value, whereas Gauss-Seidel, it updates the solution every level, and the relaxation techniques are used to accelerate the convergence. So this is a Jacobi iteration. If you see the Jacobi iteration, it uses always the initial values. But in contrast, Gauss-Seidel method, it uses the latest values. So you can just see that is the latest value. So when you look at the successive over-relaxation method, this is how the structure. So we are just there is a correction term. Our objective is to either minimize or make the correction term to 0. Then the two iteration level solutions will be same. So I just consider a research problem where you have this. These are the three basic laws which are governing the fluid flow and heat transfer problem. So the first one is conservation of mass, conservation of momentum, and this is the conservation of energy. I just took the general equation, and here I just consider a two-dimensional flow problem, a plane geometry, where you have the red portion is a hot. Your objective is to move along the hot wall. I want to find out what is the effect of the location and size. So this process can be governed by these laws: temperature equation, vorticity, stream function, velocity stream function. And the heat transfer rate is given by the Nusselt number. So this I applied a finite difference technique. This practical problem, I just gave the derivation of finite difference equation. You get a equation like this, where the coefficients are the functions of the non-dimensional parameter as well as the geometrical parameters. This is a method I used, and this is the flow and thermal distribution inside the plane geometry. And this is our simulation where the solutions are captured at every transient time level till the solution reaches steady state, and that will be put in the form of a movie. This will give an idea how the fluid flow takes place depending upon the location. So here the heat source is located at the bottom, this is at the middle, and this is at the top. This is the isotherm variation, the isotherm temperature contours for 3 different locations of the thermal source. So this will give you a better idea how a fluid flow and temperature distribution takes place at every plane. Okay, and this is a quantitative measure of the heat transport. We considered totally around 7 locations. Out of that, we found that the location somewhere closer to the middle wall, just below the uh, middle of the inner wall, gives the higher heat transfer rate. Okay. So finally, I would end the note with this. Engineering plus mathematics is everything, and engineering without mathematics is nothing. Thank you so much for your patience hearing. I would like to answer a few questions if I have time. And once again, I thank the organizers for this wonderful opportunity. Sir, thank you, sir.
Thank you, sir. Thank you. Really, your session was wonderful session, and it covered the finite different schemes, very basic at the basic level. So
Yes, sir.
I think all the faculty have made use of it, will make use of it, because they were not knowing how to apply this to engineering problems. So maybe the engineers have to look into it. I mean, so
Absolutely.
we mathematicians can tell about those schemes and all, but
Yeah.
engineers may find it difficult. So your lecture was wonderful. I don't think they have got any doubt out of it.
Thank you.
The participants can ask the questions now. I will give you 2 minutes.
Okay,
If
sir.
you have got any doubts, please ask the speaker directly.